Now, very welcome. I hope you enjoyed your short break. I will tell you a little bit now about our terahertz measurement technique that we use to evaluate aging of nuclear power plant cables. My name is Andreas Keller. I work for the Fraunhofer IZFP, the Fraunhofer Institute for Nondestructive Testing. Therefore, you can already think, yeah, this will be non-destructive testing method that I will show you here. First, I will tell you a little bit about the basics of the terahertz time domain spectroscopy that we used here. Then I will give you a brief introduction about how to do the analysis of your measurement data that you gather. After which, I will show you the practical application of the previously learned in the project Team Cables. And then I will get into a bit of a discussion of the results where we learned quite something. Now, let's start right up with the basics. And let's start here with the electromagnetic spectrum. As you can see, the terahertz area, it's commonly referred to going from 100 gigahertz up to 10 terahertz. So right at the border of microwaves up to infrared waves. The wavelength we have here, we are talking here, is in the millimeter and sub-millimeter area. Some important materials that you can distinguish in this frequency range are metals, water, and polymers. I will have a little bit of an explanation later on why this is as it is, but I will tell you right now, metals in the terahertz frequency range are total reflectors, whereas water is a very, very good or even total absorbent. Polymers, fortunately for this project, are more or less transparent, so you can shine through it with your terahertz waves and gather some information. Now, this here is our terahertz time domain spectrometer. We have here on the left side this box in the behind. This is for reflection. We have emitter and detector in the same box. In front, here on the left side, you can see our emitter for the transmission mode, and right on the other side, mirrored the detector for the transmission mode, of course, and our sample manipulator. This one moves in and out of the picture area and also up and down. It doesn't move left to right. This here on the right side, this is our signal generator. In this case, we use a femtosecond laser, and this allows us a frequency range of 0.3 up to 3 terahertz. Now, let's get to the measurement process. As you just saw, the signal generator, the laser, generates this laser pulse, which is then shown onto a beam splitter. One part of it moves up to the emitter and gets transformed into terahertz waves, which then get focused by our optics system up onto the sample. This is representative for both reflection and transmission mode, because after the sample, it again moves through an optical system, falls onto the detector where the waves are transformed into an electrical signal, an electrical current, which then can be used here for the signal analysis. The second part of the laser pulse that is sent through the beam splitter moves through a delay line. This is an electromechanical delay line, and this allows us to scan over the sample. Now, yeah, the processes we are looking at here are mainly reflection, absorption, and transmission. Of course, each and every sample absorbs more or less of the terahertz waves that that is shown upon it, and depending on that, you get reflection or more or less transmission. Additional effects, of course, that are taking place here are refraction, scattering, diffraction, and polarization, but we are focusing on reflection, transmission, and absorption. Now, our measurement process, as I have shown you just 2 slides before in the sample manipulator, it moves in the X and Y direction. So if you have this box here as a sample, you move it in X and Y direction, where the detector can scan in the Z direction, so in the depth of the sample. These are 2 exemplary signals that you get. In the top, in blue, you can see an A scan, typical A scan for the reference. As a reference, we most of the time use air in the transmission mode. Yeah, and in the lower part, you can see an A scan of a sample. First thing you notice, there is a shift, a time shift of the signals because the waves travel slower while in the sample. The time resolution we can achieve here is quite small, with 0.08 picoseconds. The lateral resolution is several orders of magnitude higher, but still fine with 1 millimeter. And we get 1,201 points of depth information per measurement point. Don't ask why, that's just how it is, stemming from the delay line. And yeah, of course, we can use this scanning system, these A scans, to then perform B, C, or D scans. Now, this is an example for our measurement evaluation program, so to say. You have here, for example, this is a tape 7125. This is measured in transmission mode, so you can imagine the detector is in. You are the detector. The emitter is just on the other side of the sample, and yeah, in transmission mode, the picture is looking like this. The scan is looking like this. And yeah, I don't want to tell you too much about this because Christopher will talk in detail about the software behind it tomorrow, but just so you can get a basic idea. Now, next up, let's move to the analysis of a sample data. On the left side, you can see a typical measurement exemplary for the terahertz frequency range. And you can see different important values. In this case, we have signal max, signal min, signal max of the time of flight here, up here, minimum time of flight, signal peak to peak. And something one should also do is using the Hilbert envelope to receive the envelope peak and the total time of flight. Because the most important values we use in the conventional method, I say conventional here because tomorrow we will learn about unconventional methods. The most important values are the envelope peak and the time of flight for sample and for the reference. This is very important. Now, I will not go into too much of a detail for the calculation of dialectic permittivity because I think Davide did a very good job just before. As you already learned, permittivity is the ability of a material to resist the formation of electric fields. The basic formula is epsilon equals epsilon r times epsilon 0, where epsilon 0 is the vacuum permittivity and epsilon r is the relative permittivity, which is a complex value. You can say it's epsilon r equals epsilon r prime times I epsilon prime prime. Now we got a little issue here. In contrast to Unibo, who are able to actually measure and calculate epsilon r prime and epsilon r prime, we can't do that with our time domain spectroscopy with this terahertz device. What we instead can measure and then calculate is the time of flight, and we can then get the relative permittivity. There are two formulas that are very important to calculate these. You can see them down here for the transmission mode and for the reflection mode. You need the speed of light. We need the delta time of flight between the sample and the reference. The delta time of flight of the maximum of the envelope. We need the thickness of a sample, and this will come into play later on. Some exemplary values for the dialectic permittivity, so you get some idea, are for metal. This is basically infinite. For water, as a good absorbent. Now you can maybe understand metal with an infinite dielectric permittivity acts as a total reflectant. Water with a almost very high permittivity absorbs a lot of the terahertz waves, and polyethylene, for example, is able to transmit. It's partly transparent. Now let's go further to the project. For the measurements in transmission mode is only possible for the tapes and sheets we looked at in this project. For the measurements in transmission mode, of course, the samples need to be accessible from both sides, as you could see in our with our machine. That's no issue at all. But as you can imagine, with the cables, they mostly have a metal shielding, right? Something like a copper mesh, for example, between the outer jacket and the insulation. And due to the reflection of the terahertz waves on the metal parts of these cables, they cannot be measured in transmission, because we are, in contrary to Unibo, we are not looking inside the cable, we are looking from the outside on the cable. But these transmission measurements of the tapes and sheets are the best way to gather all the possible information for the later modeling and for the preparation of reflection mode measurements. This is our setup for tapes and sheets in transmission. We have a 3D printed sample holder here, where we just put on the tapes or sheets. And as you can see here, we have some metal, this is aluminium tape, that we can use as a direct reference during our scanning in the reflection mode scanning. For the transmission mode, we have we just move the sample a bit to the side, and then basically we have the reference in air just next to the sample holder. Now let's look at this measurements on the cables. As I already said multiple times, we need a very good reference for each cable. Exemplary would be a metal plate that we are scanning right before looking at the cable. So we have our reflection probe head. We take one measurement with a metal plate in the exact distance that the cable will be, and then we measure the cable, and then we have reference and sample. Very important in this case is the distance of the probe to the specimen needs to be constant during the measurement. As I said, important is the time of flight, and if we are talking about picoseconds of time of a signal, then you must not move the sample in any way, because yeah, it could move this time of flight. And what Consta already said earlier in his presentation, the isolation, sorry, this is wrong, not the isolation, the outer jacket of the cables needs to be removed. So that the materials of the insulation of the twisted pair and coaxial cables can be analyzed. So ignore the fact that here it's saying isolation. This looked like this. If you, we have the coaxial cable down here. We removed the outer jacket up until the inner insulation, and the same goes for the twisted pair cables, where we of course have these 3 separate pairs and needed to have a look first which is which. This was, let me tell you that, especially difficult in the later stages of aging, because these insulations tend to have a discoloration during the aging. If we are talking about very high temperatures, then the insulation was in part fused together, and you couldn't discern anymore what if it was modification 4 or modification 7 or even just EVA or EPDM. So to eliminate the fact that or to make sure that we have our cables in a constant distance to the probe head, we constructed this sample holder here, where you can see here, this will be put on the reflection head, the reflection probe head. This is the actual sample holder where you can put in the cable, the insulation that you removed the outer jacket from, and you can clamp it down with a plate. This would be looking like this, right? This is our reflection probe head, now looking upwards, not sidewards, upwards. And this is an older sample holder, the red one, but you can clamp it down with this plate, right? And you can see here exemplary on one of these cables. And we performed 2 measurements on the cables. One right head here at the end, and one in the middle of the cable. Because sometimes you could make out some type of gradient starting from the end and going towards the middle of the cable, resulting from the aging, of course. We are currently still analyzing the data of the cable measurements, so we don't know yet if we can make out this this gradient, but we will see. Spoiler alert. Now let's get to the analysis of the results of this project. These are tapes measured in transmission mode. I'm looking at tapes in transmission mode because we have a certain thickness. This is also important. We have a certain thickness in transmission mode that we cannot transmit any waves to because they are too thick. So more or less what I'm saying is the thinner the sample, the better. That's why I'm looking at the tapes. And also in transmission mode, you have the most interaction of the terahertz waves with the material. So most possible absorption by certain materials. On the left side, we can see initial state and modification 1. Just a reminder, modification 1 means this is just pure XLPE, maybe with some antioxidants left over from the production, but mostly pure XLPE without any additional antioxidants or flame retardant. On the right side, we can see modification 4. This is XLPE with additional antioxidant from Ergonox. so phenolic and thioether antioxidant, right? And what we are looking at here are the samples aged with radiation, because the results of the radiation aged samples were the better ones. They were still not that good, as I will get to now. As you can see, we have here different radiation aged samples. In black, you have the low dose rate, in red, the medium dose rate, and in green, the high dose rate. Now, the expectation, right, would be that in the unaged, in the pure XLPE, the radiation will age the sample, and you will have maybe a gradual change of permittivity into one direction. Maybe it goes up, maybe it goes down. As Davide said, there are some reactions going on. Maybe dipolar groups are being generated during this aging, and they should be detectable in some kind. But as you can see here, the samples, the measurements are pretty chaotic, right? We have, for the low modification, it starts at the same, exactly the same value as the initial state. Although it already goes. Now you could say, okay, maybe there was some factory antioxidant in there, so nothing changed. Then there is a big jump in permittivity, and then it goes down again, even below the initial value. And this pattern doesn't repeat with other measurements. For the medium dose rate, you have, it stays almost at the same value for the first measurement, then it jumps up and then a little bit down and goes up again. For the green one, for the high dose rate, it stays almost constant. A bit weird, in my opinion. Now, if we are looking at the modification 4, so the modification with antioxidants, we would expect every value to be constant, or at least the first values to be constant to the initial state, the same, equal to the initial state, as, of course, the function of an antioxidant is to just stop the aging, or to not allow aging. So the material should remain the same mostly. So it should remain at the same permittivity. And that's kind of what happens. But still, you have jumps like here in the modification 4 with the low dose rate from 2.05 in the permittivity up to 2.2, where it stays constant. And also, you need to look at the error bars, right? These can move the value up and down quite a bit. Now, if we look at modification 7, so with all antioxidants and also add a flame retardant, the first thing we notice, I will just jump a bit between the slides, the values increase. That's just flat out, you can see that directly. That's not an issue. And the reason for that is ATH, the flame retardant. ATH is aluminum trihydrate, so it is containing metal, and we learned metals are good reflectors. So we are mainly sensitive for the ATH in this case. And everything else we could maybe see in this conventional method kind of gets thrown under the bus, because you mostly can see the ATH. And also, again, we would expect, since we have both antioxidants, the values to remain constant during the aging. But this is not the case. They jump up and down, like whatever they do, we don't know. It's curious, and again, the error bars are quite high, and that didn't ring right with us. We wanted to do something about that in this conventional method. So yeah, first little conclusion: the most detectable effects, as I said, are caused by the ATH. And we have one issue here. As I said before, we can only compute the relative value of the permittivity. But as you just learned in the presentation before from Davide, most effects are visible in the imaginary part of the permittivity, of the complex permittivity. But this just cannot be measured separately by the terahertz device. We only get the total value of the real permittivity. So what did we do? First, to at least decrease the error bars a bit, we did two things. First, we moved all the peaks to one value, because you had sometimes during because of the terahertz device, sometimes because of the measurement, you had these measurements, and they were the peaks of the maximum. They were shifted a bit to the left, a bit to the right. So we couldn't make out at first why, but we then went about and thought a bit more about it. We found the issue being the machine, and we did a rolling compensation, which means you just take this signal, right, and you move it to the right. So let's say you move the peak, the maximum of 600, the maximum of the signal to 600 samples, and everything that would be cut off or would be shifted to the right here, you just add on the left side. This is to not lose any of the signal, because this will be very important later on in the unconventional method that you will hear about more tomorrow. So this is already a bit unconventional, right? You have a signal, you cut off the later half and you add it in front, but in this case, it's fine. Yeah, and something else we did was a little normalization, where we took the amplitude of the sample and the amplitude of the reference, and we used this formula to normalize it. But still, here you can see the permittivities in arbitrary units of quite a bunch of sheets in this case. The first thing you can notice, of course, here the later values are for material 5, 6, and 7. So the materials with ATH. So again, you can see, okay, ATH is very well detectable, but aging effects, let's say for samples of modification 1, are not really detectable in this case, right? Sample 1 and modification 2, modification 4, they are in the same area, again, with these big error bars. Now, we thought about it a bit more, and we found an issue. Remember what I said about the thickness of a sample? Now, let's look at this formula again. For the permittivity, to calculate the permittivity, we need the delta time of flight, right? We are, with the delta time of flight, we are pretty sure that we don't move the sample, because we have this sample holder. in reflection and in transmission for cables and for tapes and sheets. But the mean of the standard deviation is in the area of the power 10 to the power of minus 12 seconds, right? Now, if we look at the thickness has a standard deviation of 10 to the power of minus 3 meters. This is an issue because if you have only slight deviations in the thickness, it can mean that the permittivity changes by a lot, by several orders of magnitude, compared to a little change in the standard deviation. So yeah, we mostly ruled out that method after that. Little conclusion, yeah, the thickness has a greater impact on the permittivity calculation than the time of flight. And as I said, due to the error bars, it's difficult to differentiate between the samples based just on the permittivities. Now, we thought about the solution a bit. The thickness measurement is since then done with a micrometer screw instead of a caliper. More positions are being measured and averaged, but yeah, still we have this this mean error, this standard deviation. It will, of course, be included in the permittivity calculations for remaining samples. This was a while ago. But as a complete conclusion, we can say with the conventional method that most detectable effects are produced by the flame retardant ATH due to being metal, and only the relative value of the permittivity can be calculated, also in a whole different frequency area than Unibo is working, of course. And most of the effects that are detectable in the imaginary part, as Davide showed. Now, the sensitivity to aging effects, of course, is overshadowed, as we just saw, by the deviations in measurements of the sample thickness. Keep in mind, this is all for the conventional method. It's difficult to analyze with this conventional method, but research came to our rescue, and we found machine learning methods, and these proved to be effective here. And little spoiler alert, we could in fact differentiate between different samples and modifications via these machine learning methods, because these methods are able to find differences a human simply cannot. Humans are able to find patterns, yes, but if we are talking about really small changes in signals, if we're talking about power to the -8, it's very difficult for a human to find these errors, but the machine learning can do that, and Christopher will show you that tomorrow in his presentation. That's it from me today, and if you have any questions, feel free to post them now, and I hope it was interesting.
So now it's time for questions. Thank you, Andreas, for your presentation.
Yeah, I think I have two questions. When you talk about permittivity, are we really sure that the permittivity that you estimate with your technique has the same physical meaning than the permittivity that is possible to estimate by dielectric spectroscopy or not? Is it really the same physical parameter in both cases or not?
It should be, but in a completely different frequency area, right? Because Davide and Simone, they looked at the dielectric permittivity starting from hertz up to I think 10 to the power of 6 hertz, right? And we are starting at gigahertz and going up to the 2 terahertz. So if you are increasing the frequency, high frequency electromagnetic waves are doing funny stuff. So, yeah.
But the range is almost more or less the same. So here between 2 and 3 for the relative frequency. So for the magnitude, we only measure the magnitude.
Yeah, we are talking about gigahertz to terahertz, so 10 to the power of 9 up until 10 to the power of 12 hertz. And David and Simone measured from 10 to the power of 0, 1 to 10 to the power of 6. Yeah. Okay. Second question.
In order to highlight the impact of thickness of your sample, did you try to plot the two-dimension cartography of your sample at the initial stage typically? Because you show us on your experimental device, you can displace the sound in X and Y displacement, I think.
This you mean?
Yeah, in that case. Is it possible to have a two-dimension cartography of the sample in order to show the partition of permittivity?
So you mean like a cartography regarding the thickness as well?
Yeah.
In theory, yes, but we are not measuring the thickness with this method, right? We are doing that manually. That's where our big measurement error is coming in, because we are using a micrometer screw. In theory, I could imagine measuring a sample right on with the micrometer screw, just scan it by hand, for example, or use some other method like maybe a laser profilometer.
Okay. Because to calculate the permittivity value, you need to have the value of the thickness at the exact point. Okay.
Yeah.
Okay.
That's an issue, but yeah, maybe with a laser profilometer where you can get the exact thickness.
You can measure the or you can calculate the permittivity for every point in the y direction. So we can also visualize that. But in this case, we are assuming that the thickness would be the same for every xy position, and that's not in case. In fact.
So it's a local measurement at what point and not an average value about all the sample surface. Okay.
Yeah.
Okay.
Yeah.
I have a question related to that. How much is your permittivity varying depending on where you are placing your probe?
I think
those couples were referred to the space of the.
We had a standard deviation of yeah, okay. In what area did we?
Yeah, because we discussed yesterday with Sebastian, it happens that the aging is not homogeneous.
Yeah,
and can vary, I guess, a lot.
And the question was at which point we measure?
Yeah, how much is your calculation varying depending on which zone are you choosing among the sample?
I cannot say it out of mind. I just have to look at the data. But I can tell you.
Yeah, because of course, as you said, the samples are pretty inhomogeneous. You have these yellow areas in the tapes and sheets.
So the reason why part of the reason that we measure point by point, we save the files the permittivity as the average for the whole sample and also the standard deviation of it, but I need to check it.
Okay, so you do scanning throughout the sample, or just select some points?
No, we select all points.
Okay.
Yeah, we scan the complete sample. If we're talking about tapes and sheets, we scanned them completely. The cables we did not.
Okay.
For the cables, we just had these two measurement points because there is another issue coming there. If we're talking about cables, right? They are bent, right? They are bent. They are right. They are not perfectly straight. So you have a bit of an issue there because first we need to have exactly the same distance to the sample over the whole scanning process. And second, what I did not mention yet, we need to be perpendicular with our terahertz waves. And if you have this cable, that is bent, that is not perfectly straight, with a curved surface, right? It's even more important to be perfectly perpendicular. But if you just take this cable as is and place it down and you try to scan over it, of course you will maybe in 5% of the scan you will be perpendicular to the surface. We are working on that too.
So not all the points are acceptable for your measurements because you are not perpendicular in any part.
The points, that's why we built the sample holder, to keep the cable perfectly perpendicular and in the same distance. So, but that's just why we are at the moment using just 1 or 2 measurements per cable instead of just scanning the whole cable. This will be, or we hope it will be possible in the future because we are working on that. But there's a lot of work behind that because we basically have to automate the sample head, the probe head.
Yeah, that's not easy.
Yeah, exactly.
Especially in multiple axes, it might be arranged.
Yeah.
And we try to fix that or to measure that, look at how perpendicular we are. The lasers are 3 positions around the head. So we have an area and you can know how perpendicular we are. Yeah. That's one of the coordinates of ones that you have used at the moment. Okay.
When you work on the cable, are you on the transmitter mode or reflection?
Reflection mode. It's not possible to
copper.
Yeah, exactly. And also that is why we removed the outer jacket and the copper mesh, right? Okay. But it was said before in the presentation of Consta. Of course, this is not practical in the usual part. If you're thinking about just containment, right? You can't go willy-nilly into a power plant and cut up the cables and remove the outer jacket. But I think it was Dietger that said this some time ago. Electrical boxes, right? You have electrical boxes and connections of cables, and these are the areas that we could then measure on site without interrupting or without cutting up cables, right, and destroying them. Because after all, we are a non-destructive testing.
Yes, but I also remember that we discussed, because it's when you're inside a junction box, basically the cable is already
it's there.
You took it apart because you have to connect the single wires.
Yeah.
So again, is it representative for the complete cable? Do you have the hotspot there? And there's other questions that are coming.
Yeah.
But in the discussion at one point, yes, I put up a couple of pictures of typically the connection looks like in a junction box.